The parts of a suspension bridge. We have towers, and between these towers runs a main cable. This main cable is also called as a suspension cable. And from the suspension cable, we have vertical cables called as suspenders or hangers. These suspension cables are supported at the towers either by a hinge support or a roller support. Sometimes the roller is also called as a rocker support. Beyond this support, we have anchor cables. These anchor cables are anchored by an anchor block, and the span between these towers is called as the suspended span. The span between the tower and the anchorage or the approach is called as anchor span. When we hold two ends of a chain, the shape which the chain makes because of its own weight is called as a catenary shape. But when that chain is loaded with a UDL, it will take a different shape. We will try to find whether that is a parabola or an ellipse, or whether that shape has some other equation of its own form. So to find out that, we will consider a cable suspended between the points A and B separated by a distance of L. So we call that as the span of the cable L. Since this is a symmetric both with respect to the loading as well as the geometry, the maximum dip will occur exactly at half of the span, that is at a distance of L by 2 from the support A. And because of the symmetry, the vertical reaction at A as well as the vertical reaction at B will be equal. So this will be equal to half of the total load. Total load is the load intensity multiplied by the total length. So it is PL by 2. This is the value of VA and VB, both acting upwards. Now, in order to find the value of H, when we consider the horizontal equilibrium for this cable, value of HA must be equal to the HB, and both of these must act in opposite directions. So we can call HA is equal to HB is equal to H, or simply the horizontal force in this cable, or horizontal thrust due to this cable. This cable does not take any moments anywhere. So when we take moment about any point, let us consider the maximum dip point as C. So when we take moment about C, its value must be equal to 0. Moment at C must be equal to 0. Let us consider to the left of the section. So to the left of the section, we have VA, which is acting at a distance of L by 2. VA is acting upwards, and we have this small p, which is acting over a distance of L by 2 in the left half of the span, and its equivalent will be at a distance of L by 4 from C. And we have H acting at A, and this is acting at a vertical distance of small d from C. So sum of these moments must be equal to 0. Remember, we are trying to establish the value of H now. So we will keep H on the left hand side of the equation and move the rest of the things to the right hand side of the equation. So we can write H is equal to PL square divided by 8 minus the value of VA is PL by 2. So it will be PL square by 4 minus PL square by 4 whole divided by, we have D as coefficient of H. So this value will be and we have a minus sign for this H, so this will become minus and this will become plus. So this is PL square by 8D. So the value of the horizontal reaction H is PL square by 8D. Now we will consider any random section X acting at a distance of small x from the left support. Let me consider this as the section x. This is acting at a distance of small x from the left support, and the dip at this point x, let it be d1. We will try to find the value of this d1. When I consider moment about that section x, it must be equal to VA is acting at a distance of small x from the section considered, and we have the load intensity acting over distance of x, and its equivalent is at a distance of x by 2 from the section considered, and we have h acting at a distance of d1, and this must be equal to 0 because in a cable we do not have any moment resistance, so the moment value at any section must be equal to 0. We will consider d1 on the left hand side of the equation, and we will move rest of the things to the right hand side of the equation. So d1 can be written as VA into x minus px square by 2 the whole divided by h. We know the value of VA and h. VA is PL by 2. VA is PL divided by 2 multiplied by x minus px square divided by 2 the whole divided by the value of h is PL square by 8d. So this is PL square divided by 8d. So here we have P in the numerator as well as in the denominator. I will club the rest of the things. I will take half as a common term on the numerator. So it is Lx minus x square, and in the denominator I am having L square divided by 8d. Denominator of denominator will become the numerator, so this will become 4d divided by L square. I can take x out of these brackets, so this will become x into L minus x. So this is the dip at any random section considered. So this gives the equation of the cable profile. This is nothing but the equation of a parabola. In order to find the tension at A and B, we already know the values of VA, VB and H. Since in this case A and B are both at the same levels, the value of VA and VB are going to be equal, so the value of TA and TB are also going to be equal. So we can consider the value of TA is equal to TB is equal to T, so it can be written as square root of VA square plus H square. The value of VA is PL by 2 and H is PL square by 8D. We can simplify this by taking the PL by 2 whole square as a common of these two terms, and the PL by 2 can be taken out of this square root, and we know that PL by 2 is nothing but VA or VB. We can simply represent that as V, and the remaining term within the bracket is the second term. It will be L by 16 D square. Similarly, if we try to take out the H term, H is nothing but a PL square divided by 8D, so the second term will become 1, and the first term it needs an additional 4D divided by L. So this will become 16D square by L square as the first term plus 1. Then we take H out. So T can be written as B into square root of 1 plus L by 16D square, or T can be determined using the expression H into square root of 16D square by L square plus 1. The inclination of this TA or TB with respect to horizontal, if we express that as a theta s, it can be written as tan inverse of horizontal by vertical. Because our theta is with respect to the vertical, we have to write a horizontal in the numerator and vertical in the denominator. And when we substitute the values of h and v, we get this as a tan inverse of our h is a pl square divided by 8d, and the value of v is pl by 2. So we have p and l in the denominator as well as in the numerator, and we have 2 in the denominator and 8 in the numerator. So it will be l divided by 4d. So we can write theta s, which is the inclination of the tension with respect to the vertical, as tan inverse of L divided by 4D. Now we will find the length of this cable. We will consider one half of the cable from C to B. When we consider just a very small segmental element of this cable, the length of the elemental cable can be written as a ds, and this ds can be approximately be equal to square root of dx square plus dy square. When I take dx square out of this square root, I can rewrite this as a dx into square root of 1 plus dy by dx whole square. And since I am considering only one half of this cable, I can write the shape of this cable as y is equal to kx square, where the value of k is 4d by l square, the equation of a parabola with the origin at C. So the expression for this one half of the cable is y is equal to 4d by l square into x square. When I differentiate this with respect to x, I will get dy by dx as 8 dx by l square. I will substitute this dy by dx in the expression for ds. So ds is written as dx into square root of 1 plus 8 dx by l square, the whole square. So the total length of the cable S can be written as 2 into integral ds, where we have written this ds just for one half of the section. So we are multiplying this with the 2 so that we will get the total length of the curve. And now I will replace this ds with the previous expression. So it is a dx multiplied by 1 plus 64d square x square by l power 4, the whole power 1 by 2. Instead of writing dx initially, I have to write this dx later this term, because this term involves x square. And since this is in the square root, I can use the binomial expansion, and I will ignore higher order terms. So this can be written simply as 1 plus 1 by 2 times this whole thing. And when I integrate, I will get 2 times x plus 1 by 2 into 64 d square x cube divided by 3 l power 4, and the range is from 0 to l by 2. When I substitute the upper limit, I'm getting the value as s is equal to l plus 8 d square by 3l. The lower limit is just 0, and both these terms will become zeros. So the value of the total length of the cable S is given by L plus 8 d square by 3L.